Good morning. Welcome to the GATE video. Let us, myself, Visalakshi from the Computer Science Department, belongs to the SA Engineering College. Let us start my video. So before going to the depth of the subject, let me say what is a data. Data is nothing but a raw facts. When we collect some data, we need some information that should be in a meaningful way, and the information should be retrieved properly. So here, when I say data structures, to organize the data, manage the data, and efficiently update the data in a correct order. So when we want to do all the requirements, data structure is required for a programming language. When we want to say some requirements of data, it should need a procedural, structural, functional way to represent the data in a program. So an algorithm is a step-by-step procedure to process the requirements of the required task and form in a data structure. Now we go for classification of data structures. When I say classifications, we classify into primitive and non-primitive data structures. Primitive data structures, here it has been classified into integer, character, float, and pointers, and that has been further classified into non-primitive data structures, and a non-primitive is broadly classified into linear, non-linear, and arrays, list, linear data structures, and non-linear data structures. We will be elaborately saying what all these, and we go in depth with the concepts. So when I say primitive data types is nothing but when you want to do some operations in a machines, we instruct the machines to do some actions. So when I say an integer is nothing but a whole values, and the values which are assigned with the data type integer. So then floating point, it contains the values with decimal values, and the numbers of characters, it can be a single character, and the values can also be assigned, and the pointers is indicated by the asterisk to represent the storage address location where the required data is to be stored. Then non-primitive data structures, it's a linear data structures, and we organize the data, and here the concepts in linear data structures related to stack, queue, and linked list. And non-linear data structures, we also discuss with the topics of trees and graphs. As we say in the linear data structure, stack is the requirements of data stored in an organized way, and that data should be in a format of organizing, that is first come first serve. Then the queue, when I say, is last in first out, that is last data whichever been. Best example is banking transaction. For stack, the best example is a list of books in my hand. I have the last data which I placed, that one will be removed first. Then here we go into the concepts of graph is the topic which related to non-linear data structures. So when I say a graph, it's a relationship between the data, and the graph is denoted by the letter G. G is equal to V comma E. V represents the vertices and E represents the edges. Here you can see each and every node is connected to the particular edges, and they show that they are connected and there is a relationship among the nodes present in the data. Then here property of a graph, we say just directed graph is nothing but no cycles. When it is undirected, we say it is no cycle is formed in the particular tree structure, and the nodes property of this graph is nothing but nodes exactly have n-1 nodes, and the undirected node must have at least n-1 edges. Graph traversal algorithm, it is nothing but the algorithm, it has several categories of classifying the pre-order, in-order, post-order of the tree concepts. Now we represent the graph traversal using breadth first search, that is the elements that is to be connected to the nodes, and it has to visit all the nodes exactly at least once. And we see about two basic concepts here, depth first search and breadth first search. Breadth first search related with the queue concepts, depth first search with the stack concepts. Here depth first search is also deeply inbuilt with the requirements of the graph, and it has to track all the nodes, it has to visit all the nodes exactly once. Breadth first is similar to that, but it has to visit adjacent nodes based on the concepts of queue. Here we say some examples of graphs here. Molecular structure of all the nodes being connected. So here we can say this is an example for a graph, as well as the network of several terminals is being connected is also an example of graphs. Next we have the definition of the graph. For each node E and V, the set of, we denote the edges with the letter E, and a graph is related with the capital letter G, and a pair of vertices V comma E. And adjacent nodes, the nodes which are from the requirements of the adjacent nodes, U and V are connected with the set of edges. U and V are adjacent and W is not adjacent, as in the diagram I have shown. Path is a simple requirements where the nodes and the edges being connected. So here edges V1 and V2 are connected, V3 and V2 and V3 are connected, and V3 and V4. Similarly, we have make a simple path and connect all the pair of edges and the nodes being connected. So let us say it is a simple path. So when I say cycle is nothing but a complete rotation of all the nodes and the vertices appear at least once, and it has to visit it. Then when I say a connected graph, when the requirements of the nodes of the path, every node are existing and they are, otherwise it will be disconnected. Complete graph, here I have shown you 3 nodes which has been completely connected, and here another set of nodes, 4 nodes being connected here. And weighted graph is nothing but all the requirements of the nodes being specified with the characters, numbers or letters. Here I have just specified some country names, and weights is also assigned. Some values are assigned on the sides, so represents it as a weighted graph. Here problems related to graph. So here various concepts of problem related graphs are there. Graph traversal, topological sorting, spanning, minimum spanning tree, and shortest path are various problems related to graph. Now we will be discussing about the first question. Here suppose we have to find out the breadth first search of the root and undirected graph. Here a set of nodes has been connected from the level 0, level 1, level 2, level 3, like that, level 1, level 2, level 3, level 4. Based on the levels or the requirements of the vertices being represented in the undirected graph, here certain options we have to find out which cannot be the edges in the original graphs. As by the depth first search we discussed here, based on the levels of the undirected representation, we have to check whether the nodes from the root from the left or right, we have to assign, I have to place all the nodes in the graph. Then we have to check whether the requirements of 8 and 11, here the requirements of the letter, the number is 8, is in the lower level. That has been connected with the requirements of the uppermost level at level 3, then that has been connected, and here in the B option 3, the level, it has been present in the middle level, and that has been connected to the number 10, that has been the topmost level. So second option is not possible, and let us see the third option. The node 4 and 5 has been 4 and 5 are connected in the same level of strategy, so this strategy is also not possible for connecting the nodes, original graph. Then 6 and 9 has been presented here, the requirements, and the 9 is also in the same level. So the connected edges of the original graph, the correct answer is option is A, 8, 11. Then next question, suppose consider an undirected connected graph with the vertices and edges in a graph. We have to find out which one of the statement is correct. So here in the first option, O of m plus n, if we want to find the time complexity of the algorithm based on the undirected graph, so here the first option is to find the minimum spanning tree performing the breadth first search. So breadth first search related to the Q concepts of the algorithm, the minimum spanning tree. Here the m and n are the vertices and edges being connected. So in the breadth first search, the requirements of the concept of the algorithm is possible to find in the first option. Then let us see the second option of answer, a minimum spanning tree that can be found with the Kruskal's and prims. Here in the minimum spanning tree, we can also follow the concepts of Kruskal and prims, but here it is specifically asked that it can be compensated with breadth first search. No, this second option is not at all possible. Then third is unique minimum spanning tree. The edges of the weights are not equal here, so it is not unique. So this third option is also not possible. The fourth option, depth first search always produce spanning tree. Here it strictly follows the concept of total weight with the minimum spanning tree. This option is also false. So the correct option is A. Third question, the number of spanning trees, a complete graph. Here you have 4 vertices and the label with A, B, C, D. So here n number of vertices are present. Based on the Kaliman theorem, here we will say that complete graph for the vertices is 4n. So n is equal to 4. So n into 2n. So 4 to the power 2. So the answer of this option is 16. Answer is 16. Then let us see this directed graph. Let G be a directed graph for the depth first search. That is the spanning tree of the root. Here we have to say that T of the breadth first search in the graph that is to be visited, and which of the following statement is true in the graph of a tree. So here there are no backtracking edges with respect to the tree. So this concept is satisfied with the breadth first search. So this option is possible. So option A is true. Then we'll see that there is no cross edges with respect to tree. Here there is a possibility of cross edges, but the requirements here you are saying is vertex of the root of the spanning tree should match. So no cross edges is possible, no backtracking is possible. So the option true B is false. There is no forward edges with respect to tree. This is also forward, and in the concept of depth first search and breadth first search, the forward edge concepts of the tree is not possible suited with this question. So the third option is also false. The only edges in the graphs of the edges in tree. So this is not possible with all the edges. So only one edges they are specified. So it is not possible. So the correct option is A. Then the traversals of undirected graph here using 100 and the vertices is 40. So the number of connected components in this requirement is, so the total number of vertices is 100 and the total number of graphs is 100 and vertices is 40. So in the undirected requirements, so edges is equal to V minus C, vertices, so 100 minus connected components 40. So 100 minus 40, the answer is connected components of G is 60. So the answer is 60. So here another one, here we are seeing the requirements of vertices and edges being undirected on the weighted path is 100, and the D is the number of edges in the shortest path. So maximum number of overall pairs belongs to the set of elements is 30. So we have to find the diameter of all the graphs is 30. So triple T denotes the depth of the breadth first search of the entire tree of the graph. So the height of the requirements is 60. Here we have 30 and the requirements is 100. So we have to specify the exactly height of the requirements, and we have to find the depth first search concepts of unweighted and directed. So the first option is correct, and the height of triple T is exactly 30. So it is not equal to the requirements of the number of edges. So the second option is not possible, and the third option is height of the triple T is at least 3. So the requirements is not equal to the requirement, or the requirements of the U and V is equal to V. Then this third option is also not possible in the graph. Then the height of triple T is at least 30. So maximum number of requirements and the requirements of 30 is not equal. So the fourth option is not possible. So the exact answer is A. Thank you. Welcome. We'll just return back in the next video. Let us meet in next video. Thank you.